Hi everyone, I wanted to talk a little bit about integration and looking at cross-sectional areas. So to start off, I'd like us to visualize a 3D object, and at the base of the object is a square. The top surface of this object is like a dome, and it's made up of these circular arcs which have a radius of 20. Now, I've also given you some information about the density of the material, but we'll deal with that later. Now, at any given height above the base, and I'll call that little h, my cross-sectional area is a square, and I want to understand something about the relationship of the height and the area of these squares and the radius, so I want to put all these pieces together. So one way to do that is to look at my height, and I've shown that here with the elevation off of the base. Okay, so that's my height. Then we've got from the center of the square, we can go out to the edge, and I'll call that D, the distance. And then I've also got another side length of a triangle here, which I could call R, and R we know is 20. So let me add that to the diagram here. R equals 20. And that is indeed the radius, right? Because I'm going from the center out here, and I'm given that that radius is always 20. So no matter how I go out, it's a radius of 20. So now what I have is I have a little right triangle there, and I could set up an equation of a right triangle, which would be h squared plus d squared equals 20 squared. So what this would allow me to do is solve for d. So let's see, I'll bring over my h squared, and then I'll take the square root. D cannot be negative, so I don't need to write plus or minus. Normally I would, but in this case I know d is positive, so I'll just say that this is the square root of 20 squared minus h squared. And that gives me a representation for that little length d. Now, I've got another triangle up here in this picture, and I'm going to exploit that one now. So I've got a side length D, which I know. I've got a side length D, which I know. And then this side I need to figure out. So let me draw this big square. I've got a big square. Okay. And in here, I've got a right angle. Each of these are side length D. And so I could figure out what is the hypotenuse. Well, I've got D squared plus D squared equals my hypotenuse squared. In other words, I've got 2 D squareds equals the hypotenuse squared. So that means that this side length over here would be, I take the square root of both sides, it would be the square root of 2d. So now we know what is this outer edge. This is the square root of 2d. Why is that important? Well, now we can calculate the area of the cross section. And remember, it's a square. And I figured out the side length, right? The length of one side of my square is the square root of d. So I need, the square root of 2 times d. So I need the square root of 2 times d squared. That gives me 2d squared is the area of a cross section. Furthermore, that d, I know that d is a function of h, and I have solved that over here. So I'm making some good progress Now, what would be next? So the next thing we could think about here is how would we find the volume of a little wedge. So if we take a volume of one of these cross-sectional pieces. So we have a square, and let's suppose it has a little thickness to it. So that little thickness there I'm going to call delta H. So I need to do volume would be delta H times the surface area. So my volume is going to be area times delta H. So if I know what my area is over here, 2d squared, now I can add this to the list of things I know. I know my volume